Today's talk is going to be a bit different, perhaps from a lot of the talks that you've seen, which have been focusing on hard matter kind of materials design problems. I do soft matter research, and you'll see some of the complexity that adds to the concept of workflows. Before I get started, I just want to acknowledge the people that did the work because we might run over. It's been an excellent discussion thus far, but I am fully anticipating getting sidetracked by you all. And so in the context of current group members that are working on the projects you'll see today, Jackson Elowit and Joshua Bilski have been working on this, as well as Leonardo and Swaroop. A lot of the older references that you'll see from the last couple years were done by Michael Service, as well as, where is NB Swajit Sadhu. In particular, one of the projects that I'm going to spend a lot of time on in the context of kind of persistent homology for energy landscapes was part of a really fantastic collaboration with Henry Adams at Colorado State, who actually just moved to the University of Florida, and his PhD student, Brittany Story, who worked with myself and B. Swajit on that project, and that was funded by NSF as part of a Harnessing the Data Revolution grant. So I'm hoping that you'll find some complementarity with Jorg and Jan's talk on Monday. And I didn't get here until Monday night, so I watched the YouTube videos last night. And so I tentatively, I think, got approval from Jorg to take Snapchat from his YouTube when I was to take a screen snapshot of it. Where he really did a lovely job introducing the methodological challenges associated with hard matter materials design in the context of exploring the configurational space, and really putting it in the context of the partition functions associated with that configurational space. Now, when we think about crystalline systems, those contributions to the partition functions are pretty easy to kind of write in the context of chemically meaningful states, whether those vibrational, rotational, electronic, configurational type contributions. But in the realm of soft matter, if we ignore things like liquid crystals that are a bit odd, these are very heterogeneous systems. If we're talking about like gels, or if we're talking about complex multi-component fluids, polymers, these are very heterogeneous systems that are intrinsically disordered and have varying length scale correlations, which means that kind of configurational state concept becomes a bit harder to quantify. And they have very distinct correlation times that can be multi-time scale phenomena associated with how easy it is to escape minima that maybe are lots of low-lying minima on the potential energy landscape versus large barriers for large configurational changes. Another key aspect of soft matter materials is that the dynamic phenomena are actually kind of an intrinsic property of interest. And so we don't want to ignore the dynamic fluctuations in these systems. So a really nice example of this are microemulsions, which I do a lot of work on. And these have very complex and rich phase diagrams where we have a surfactant, which is an amphiphilic molecule that is in an organic phase mixed with water. And so depending upon the ratio of surfactant, oil, and water, you can have kind of this whole range of phase transitions where initially you might have an oil and water mix, which is characterized by what's called a Windsor 1 phase, where you have these oil kind of micellular structures distributed in the aqueous medium. You keep on adding water and you'll get to kind of like a lamellar phase where you have an equilibrium between the oil and water phase. You add a little bit more water, you get a phase separation, and now you've got an oil and water microemulsion. And then if you add a little bit more water, then you can have a out of equilibrium kind of oil and water Windsor 4 phase. And this is kind of shown in this phase diagram here. And so I want to kind of bring to bear kind of a different perspective on thinking about some of this partition, kind of the partition function as a way to mathematically connect the structural distributions of all these different states and the energies biased by the energy distribution. And so let's just be a little bit agnostic and think about any kind of energy landscape. Oftentimes when you think about we're going to do a DFT calculation or we're going to do an energy minimization with some type of approximate Hamiltonian, we're often trying to find the global minimum. But if we're talking about sampling configurational space, then this means that we're trying to find all of the relevant local minima that may be populated under a given set of temperature, pressure kind of conditions. And these are what we would call the index 0 critical points. But if we want to sample fluctuations, then we need to sample the barriers, right? And so we need both the maxima and the minima. And this would mean then that you would need to know the positions of all the index 1 critical points and sometimes even higher order critical points. I'll show an example later on in the talk of some recent work that's indicated that index 2 critical point pathways can be important in some types of reactions. And so there's a key challenge, I think, in soft matter research of how you connect the ensemble distribution, how you identify, number one, all of these configurational states. Two, once you have that identification, you have this distribution. How do you connect this distribution to the underlying energy landscape in some dimensionality representation? And so you can imagine, maybe you've got some really complex self-assembly kind of distribution of superclusters and primary clusters and monomeric building blocks, and you can, create some descriptors that allow you to define a distribution of these species. And we want to be able to seamlessly try and link this to some underlying energy landscape. And choose the right dimensionality representation of that landscape, because it's not just going to be, simple geometric coordinates. And so, this notion that this energy landscape is this nice, simple, low-dimensional space is a lie. And we need to figure out ways to encode higher dimensional features of the energy landscape that allow us to really map well the energy, the shape and topology of the energy landscape between very complex transformations between these really complicated kind of states. And so if we wanted to think about how we might have a workflow for soft matter design, and I am not a workflow person, but this was kind of my vision here. If there are certainly people that are synthesizing and characterizing soft matter systems, and they characterize it using X-ray and neutron scattering and things like electron reflectivity, stuff like that. And obviously, you want to be able to take that information, and eventually you would want to try to do some kind of decision-making process associated with the properties of that soft matter system, to optimize those properties, keeping in mind the dynamic behavior of that soft matter system, right, in some rational way, the same way that you would do in a crystalline system for many of the workflows we've seen before. And the question is just, what do you need in the middle here? And we've seen a lot of examples thus far about putting, DFT calculations, very beautiful scientific kind of computational workflows in this interim that then allows you to do this decision-making process. And so you might be inclined to do something like borrow methods from biophysics for this purpose. And I want to use this example. I'm going to try and go through it really quick. So I'm going to ask you not to ask any questions about this because I don't want to get sidetracked. It'll throw off my timing. But I'm happy to answer questions at the end on this particular subsection. But you might be inclined to do some kind of Markov modeling, right? To try and connect structure and energy. And a really nice example that we're going to put on the archive actually next week, it's almost ready, is in the case of microemulsions, where you've got this amphiphilic surfactant molecule. And we've noticed in several prior papers that if you have this amphiphilic molecule in oil and you add water and acid, by changing the variations of the concentrations of water and acid, you can change the micelle size really significantly. And so the question is, what's the molecular origin of this change in micelle size and the microemulsion? And can we reduce the dimensionality of that energy landscape associated with this, with whatever the underlying physics is that's leading to these changes in micelle sizes to be conceptually meaningful? And so if you think about a Markov model approach, right, a Markov model approach is actually quite complicated, but you start off with your molecular dynamics trajectory, you do some kind of featurization with order parameters, then you do dimensionality reduction, then you do some kind of discretization, then you generate a transition matrix to create your Markov state model, then you analyze it to get some kind of energy description by looking at the flux. And so we did this. And just really quickly, the point here is to show you that this whole Markov approach is very, very time-consuming and hard. And so if we just do something, and it's not necessarily as meaning, it requires a lot of manual intervention. So if we take this molecule, we have to come up with some kind of feature descriptors, and we might come up with a whole series of distances and angle parameters, and then you need to evaluate them in some way by maybe using VAMP scores. And then once you figure out which features are capturing most of the changes in conformations of this molecule as it relates to the micellular size, then you would do some kind of dimensionality reduction with TICA or PCA. And if we did this, let's say we use that one feature which is based upon distances, and we look at, we're trying to keep as much of the variance as possible as it relates to the conformational floppiness of these molecules in these solutions. You keep a very large number of dimensions here. We're in like 20-dimensional space under conditions where we modulate the amount of acid. So we go from a non-polar solution where there's no acid and water to a polar solution where we've added acid and water. And as we add that acid and water, it grows these micelles. And we're trying to relate the conformations of these molecules under these polar conditions to the aggregation phenomena. So now that we've done that, we've got now these 22 dimensions. We need to discretize these states associated with these conformations of these molecules in the micelles. And when you do that, you actually have to go through a whole series of benchmarking kind of processes, right? You have to look at the implied relaxation times and make sure that they're well separated, and then go through a Chapman-Golgorov test. And then finally, you've gone through this discretization workflow, and you get these macro states, right, that are meant to represent kind of what groupings of conformations of these molecules are most related to specific micelle type of sizes and behaviors. And then you can generate this transition matrix between those macro states. And when you do that now, we can get at an energy landscape associated with these macro states. And these are the macro states that are populated in some of the conformations of these molecules that are populated under conditions where we have no acid and water versus when we have acid and water. And you'll see that the energetics of these states are very, very similar. And you might be inclined to say, oh, well, there's no effect at all of the polarity of these extra added water and acid molecules upon the free energy landscapes of the conformations of these surfactants. But if you start looking at the fluxes and the committer probabilities, there's actually very big differences in the transition probabilities going between these states. And so this indicates to you that maybe there's something different going on there. And so we start to then look at the structures and configurations in these macro states, and they're actually very, very different. And so it turns out that when you add acid and water, you change the conformations of this molecule that are observed in the solution, and you get way more eclipsed conformations than in nonpolar conditions where there's no water and acid. And in fact, if you then do something like well-tempered metadynamics to actually probe the conformational energies in the presence of these polar molecules versus nonpolar molecules, you see that you in fact change the energy landscape. But this is all done manually, right? And so all this whole process associated with trying to connect kind of structure to energy in this soft matter system is very hard and tedious, and it takes a long time, and it doesn't scale easily with multi-scale processes, multiple time scale processes in a system. So it doesn't scale easily across space and time. And so the main part of my talk, and this whole last part, you can ask as many questions as you want. The main part of my talk is really about alternative approaches to define states, configurational states in soft matter systems, and connecting them to underlying energy landscapes. And for this purpose, we're really turning to graph theory and topological data analysis as that tool for encoding this information. And so we're going to primarily talk about point cloud data, but we'll also talk about functions and manifolds. And the first aspect of what I'm going to talk about is the connection between point cloud data and networks or graphs. And this has a very, very long history in chemistry. We've seen lots of graphs already in the context of different types of molecular descriptors. It dates back to the 1870s, where Arthur Cayley was first trying to enumerate all possible alkanes based upon tree diagrams. That was very effective, but it also, then led into things like trying to find, chemical reaction mechanisms based upon minimal edge deletions and insertions of adjacency matrices that dated, back to this concept in the 1850s about the principle of minimal structure change, as well as things like quantum wires and quantum graphs for in quantum mechanical kind of calculations. And so there's this very, very long history of molecular graphs in chemistry as a whole. And as a consequence of this, there's many, many descriptors, which I know a lot of you guys are familiar with. And these descriptors can capture both local as well as non-local patterns in graphs. And if you kind of turn towards like spectral graph theory approaches, you start to get nice global descriptors as well of connectivity patterns. And you can even connect, I would say that this is still a very active area of research, but within a very small community, you can even connect different types of topological indices to different statistical mechanical kind of theories. And so actually Ernesto Estrada has been working in this area for a long time, but his academic lineage goes back to kind of the Eastern Bloc kind of pioneers of a lot of topological indices for molecular systems. And there's also been some work associated with things like relating Shannon entropy to thermodynamic entropy and things like this. So we've done a little bit of work on graph descriptors, not in the context of molecular graphs, but in the context of intermolecular interactions, where obviously if we make graphs of intermolecular interactions, then this provides a basis for us to then understand things like soft matter structure. And so we've done a bit of work on the spectral graph theory side using different types of graph theory descriptors from the PageRank algorithm to actually invoking and using these actually as collective coordinates to do biased molecular dynamic simulations to probe energy landscapes associated with chemical reactivity, as well as a few centrality measures. We've got lots and lots and lots of applications associated where we've used these graphs of intermolecular interactions to probe kind of complex multi-component soft matter solutions. What I want to focus on today is a little bit more of our more recent research, and this is where the emphasis is really upon trying to create a platform or framework for understanding kind of multiple length scale kind of encoding of structure in these solutions, and trying to come up with and use and adapt community analyses in a hierarchical way, as well as to capture the time-dependent behavior. And so from molecules to micelles, we can create these interaction networks that capture all of the intermolecular interactions in these soft matter systems, the hydrogen bond interactions, the amphiphile interactions, the amphiphile water interactions. If we have ions in there, then they can have the ion interactions. And this is just kind of a representative reverse micellular structure that you can actually very easily identify from these networks using something like modularity optimization. And so modularity optimization is a pretty nice tool that actually dates back a ways, but I would say that the computationally efficient algorithms kind of came out about in 2008. But basically, you're doing a cluster partitioning that is maximizing the internal connectivity of a community within this very large graph and minimizing the external connectivity that community has. And you can do it in multiple passes, right? So in the first pass of a graph, you'll identify communities that have strong interconnectivity, and then you can coarse grain them into individual nodes, and then you can do it again and look at how the nodes are connected, and then you can do it again. And so you can go through this hierarchical process with modularity optimization to go from kind of a molecular micellular structure to then look at micelle-micelle interactions. And then if you wanted to kind of look and see, like, for example, how percolated the network was, you could keep on doing this coarse graining to kind of understand those internal connectivities up to different length scales. We recently adapted this to do modularity optimization in time. And so, all of this is coming back is coming down to analyzing molecular dynamics trajectories, right? And so we have time-dependent graphs of all of these intermolecular interactions. And these communities in time, because these micelles are not incredibly stable, oftentimes they'll merge and they'll split. They might kind of completely break apart as individual amphiphiles get sucked in and attached to other micelles. And so you have this really complex process of growth and contraction, merging and splitting, birth and death, associated with the clusters that are forming, or the communities that are forming in these systems. And so we recently came up with and adapted an approach that had just been published just a couple years ago called the delta screening approach, which was a way to analyze temporal graphs for chemical systems. We've adapted it. And basically, we now define these things which we call temporal communities, where we identify and add certain constraints associated with how much a community can change in time before it no longer is the same community. But this is a user-defined thing, which is really quite nice. And so, my cell, if we're talking about these microemulsions, my cell might have surfactants that are exchanging between them, and at some point you know, you've changed your node composition so much that it's really no longer the same chemical entity. But this uses increased, and it has actually quite good computational efficiency because it looks at the statistics of the edge deletion and additions in time and uses that as a basis for whether or not it's going to do a new modularity optimization approach. And so we've applied this to examine transport in separation systems. And so in our phase diagram of this microemulsion system, if we're kind of in this Windsor 2 phase where we have kind of this organic oil and water kind of microemulsion, if we have something like ions in the aqueous phase, these ions will interact with the surfactants in the organic phase and get transported across. And this is, and I think Ping is going to talk about this a bit tomorrow, but this is a primary way that is it's called solvent extraction, and it's a major industrial approach for separations and purification processes in aqueous or liquid phase systems. And so if we kind of apply this temporal modularity optimization approach in a dynamically transporting oil-water interface, we can very easily see groupings of basically time. These would be like lifetimes of these temporal communities that correspond to highly dynamic communities that are present just in water, because in water you've got all this hydrogen bonding that's breaking and forming, and so it's highly dynamic, really big communities. The clusters or the waters that are being actively transported and part of the interfacial region itself have characteristically different time scales. And then the waters and ions that migrate into the organic phase are very stable and intact because they're surrounded and part of this reverse micellar structure. They have very, very long lifetimes. And so it's actually kind of cool because we can actually identify and use just the dynamical kind of characteristic lifetimes of these communities as ways to pull as direct connections to kind of where they are in the chemical system and their behavior. So the next approach that I want to talk about is the formation of simplicial complexes from point cloud data. And in this context, simplicial complexes, you might be more familiar with their usage in something like UMAP or something like this. But simplicial complexes can contain quite a lot of information, and there's kind of two ways that you can think about the process of creating a simplicial complex from point cloud data. One is you just might, so the way that this actually works is you've got your point cloud data and you put basically balls on your points and you grow those balls, and as the balls grow, you form edges, and then those edges will form faces of polygons. Typically, this is done in a tetrahedral kind of format. Could also be triangular kind of format. And then, at the end, when you've got you choose some ball radius that forms this simplicial complex, and then you can analyze this simplicial complex, right? Alternatively, if you want to keep track of the information associated with the connectivity pattern in the simplicial complex, as you grow your ball radius, you can track how the components or the connectivity patterns are changing. This then leads you into something which is called persistent homology. And so here's an example where I've got point cloud data. I put balls on the point cloud data. I grow the radius of those balls. I form edges. Then I grow it more. I get more edges. Eventually, my edges, I get faces of these of the simplicial complex. I'll get holes and cycles that form until I've reached some simplicial complex at some fixed distance. But basically, these are distance filtered graphs. And I can keep track of the way in which these edges form and the holes form, and I can encode them in something called a persistence barcode. And so I can record the number of components of the simplicial complex, which is the zero-dimensional information. These are just the number of points. So here I've got a large number of components. As soon as my balls start forming edges, those components merge, and so they die. And then as I form more and more edges, I get less and less components in the zero-dimensional space. Then when I form a hole is a higher dimensional component. So then I've got a growth of a hole with the death of my beta 0. The holes are Betty 1s. And so in this persistence barcode, as I increase the radius along this axis, I can see all my initial components of all my points. Eventually, these edges form, they merge and die, and here I start to form holes. And so this is my persistence barcode, which is a fingerprint of the spatial distribution of this point cloud data, okay? And we can use this and have used it for a large number of systems. It's something we use quite regularly now, where we're trying to use the persistent homology barcodes as a fingerprint of the structures that are formed in these emulsions. Okay, so for example, here are two different surfactants that have different branching structures of these alkyl tails. This is the plot of the holes, the persistent SPEDI1 numbers versus the size of those balls, and you can, and I get very different behavior in the cycle distributions for this molecule relative to this molecule. So it's very good differentiating the different structure that's formed by the micelles of these surfactants. Now, a really beautiful thing about persistent homology is that it's not only applicable to point cloud data, it's also applicable to functions. And so if you just take a simple function like this that has, minima and maxima on this function, I can do what's called a sublevelset filtration, where I start off at the minimum of the function, and this is one component, okay? As I filter up in whatever this axis is, whatever this variable is, I'll find another component. And then as I filter up, eventually these components merge because I overcome a barrier, right? And so the filtration in whatever this variable is on my vertical axis, I can keep track of the minima and maxima. Maxima are where those components then merge as I scan upwards. And so I start off with one component, then I go upwards, I get two components, then I overcome a barrier, and these two components merge, and I now just have where's my B? There's my B1. These guys merge, so this component dies, okay? Then I go up again in whatever this axis is, I get a new component, that's this one. Then I go up, I overcome a barrier, actually I go up here, there's another component. I go up, these guys merge. I go up again, these guys merge, and I get a semi-infinite bar, which is like the single component that's left once I've filled all of whatever this filtration is. So I can do this going down. So let's say I've got this really complex function here. This is my level set. My level set are just the sets of increments associated with the function that I'm filtering. Okay, and I can start from the bottom and do a sublevel set, or I can start from the top and do a super level set and encode this information in this barcode format. So again, we have looked at this in the context of things like separations. And one of the ways in which we did this was actually through an image encoding kind of approach, where we had, if we look at these surfaces and we have these surfactants that are on these surfaces, we basically turned this into a bitmap representation where we projected the density of those surfactants of the surface onto a little grid. And so we get a density, we basically get an image of the density of the surfactant on the surface. And then we're doing sublevel set persistent homology of this bitmap representation of the density of these surfactants on the surface. And so here's some of these images associated with these density images of the surfactants on the surface. And depending upon the composition of the surface, I can go from something that looks really kind of homogeneously distributed to something that looks quite heterogeneously distributed. And I can introduce a number of descriptors associated with the persistent homology that is kind of capturing this organization on the surface. So we introduced some descriptors. We introduced a descriptor called the excess Betty curve, which is where we take the molecular dynamics data of the structures on the surface and we compare it to a purely random image that's at the same density. So we used a pretty significant, we used a random number generator to create this random image. And then the difference between the equilibrated or the molecular dynamics density distribution versus the random distribution we call the excess Betty curves. We also introduced persistent entropy or use persistent entropy. This has been introduced before, but basically this is measuring the variations in the lifetimes, the persistent lifetimes of those barcode components. And we introduced a non-ideality index for these surfaces where, if you've got a surface and these surfactants aren't interacting at all, then we know what the number of components should be on the surface. And if you have variations from that, then that's indicating that those surfactants are interacting with one another, which would be a non-ideal interaction. The cool thing about this is that these persistent homology descriptors correlate really well with known experimental data associated with the interface. And so these are plots of persistent entropy versus the surface tension under a wide range of systems. And you can see that the persistent entropy maps really well onto the surface tension. And if we take this non-ideality index that I mentioned and we compare the time-dependent evolution of the system under what we would call non-transporting conditions, where the system is basically equilibrated and nothing's going on, the distribution of the surfactants is pretty ideal. We're close to 1. If 1 is one actually should be the top of this. And then if we look at a transporting system where now you've got these surfactants that are pulling ions and water across the surface, you can see that the non-ideality index drops a lot and you have this huge range of these transporting surfaces. And so basically, you know, what we've learned thus far, if we think about these persistent homology and graph theory tools in the context of structure, of soft matter systems, is we've got a huge range of tools, right, that are capturing and have the ability to create some kind of representation of states in soft matter systems. We can do this across length scales, right? So we can do this at a local level as well as a global level. We can capture dynamic phenomena through a wide range of tools. And so now the question is okay, now I've got these tools, I want to now connect it back to that underlying energy landscape. I want to understand what the distribution is of minima and maxima that's leading to these structures, right? If I want to design an emulsion where I get specific size and shapes of my cells, or where the dynamic behavior is a property that I'm trying to optimize, I need to know that topology of that energy landscape. And so I could do this through brute force mapping along collective variables, like we did actually with our spectral graph theory descriptors PageRank. We implemented that to do biased molecular dynamics simulations. I could try to use the dynamical information of these states in a Markov type model like I showed you before, but that involves a lot of work. Or I can think about how to encode the topological information and think about patterns that are associated with the energy landscape, and maybe think about some new math tools that actually allow me to kind of having to bypass measuring the energy landscape at all. And this is what the last major part of my talk is going to focus on. And so a number of you might be familiar with compact representations of potential energy landscapes. They're used a lot in things like protein folding. And the dominant one is our disconnectivity graphs. And so disconnectivity graphs basically take the energy landscape and they follow just the index 0 and index 1 critical points. And so the index, as all the minima basically, are the leaves on the tree of this of this graph, and then the transitions between those index zeros are what are connecting those leaves. And so we could map and imagine an energy landscape that maybe looks like this, where I've got a bunch of index 0 critical points here, here, and here. Then I've got some index 1 points that maybe connect some of these 0 points. And I might even have some index 2 critical points, okay? But the disconnectivity graph, as I showed you before, for this particular energy landscape here is only mapping those index 0s and 1s, okay? And the important thing to recognize about these disconnectivity graphs is I could have two very different energy landscapes, and they can give me the exact same disconnectivity graphs, okay? And so we would like to have more information about the topology of the energy landscape than just this, this particular description. And the reason why is because we want to use, you know, because these soft matter systems are so robust and so complicated, and their energy landscapes are going to have lots and lots of features, we really want unique fingerprints, and we want to keep track of and have a really mathematically robust way to keep track of all of the features of that landscape across different dimensions. And so for this purpose, we're going to use the same sublevelset persistent homology approach that I mentioned to you earlier. So now our function is an energy landscape, okay? And this is a really simple energy landscape, but it could be any dimension, you know, any 3-dimensional energy landscape that you might think of in the context of atomic configuration space. And we start off with some minima, and I like to think about it like an energy landscape bathtub, right? And so I've got some minima on my energy landscape, and I start dumping energy into this energy landscape bathtub. And initially, all my energy goes into this minimum. As I keep on dumping energy and going through the filtration now of energy in sublevelset persistent homology, I see local minima. and another local minimum, and then I start to overcome barriers, and my components, which were my minima, start to merge. I get holes that represent really large barriers on the energy landscape. I keep on filtering up in energy, putting more and more energy into my energy landscape bathtub until it's totally full. And so the resulting persistent homology barcode for this energy landscape, I start off with my original components, and then I form my holes, and then I can actually go up, quite high in dimension. This is only a three-dimensional energy landscape, so I only have 3 sets of bars. But if I had, much higher energy landscapes, you'll see higher bars that represent higher order critical points that are being overcome on the energy landscape. And so what we want to be able to do is we want to be able to use sublevel-set persistent homology to distinguish between different potential energy landscapes, to understand chemical dynamics, and as a motivation, sometimes people say, oh, well, we only care about transition states. We don't care about any higher order features. But in fact, there are some systems where second order pathways are starting to be recognized as being relevant. So the important nice things about this approach is that allows us to visualize higher dimensional features of the energy landscape really easy. We don't have to do dimensionality reduction if we don't want to. We capture a lot more information about that potential energy landscape topology, the bar lengths of the barrier heights, the number of bars of the number of barriers. It includes all indices of all critical points across all dimensions. It creates a platform for actually quantifying differences between potential energy landscapes and their topology, which I think is incredibly relevant to chemical design. And what I'm going to focus on here is by focusing upon the patterns in energy landscape, we might be able to learn and predict new energy landscapes. And so, how much time do I have, Joshua?
You've got about 15 minutes.
Okay, perfect. I actually might even, I'm cruising. You guys didn't say a word. This is awesome. But if you have lots of questions after, okay, go ahead. Go ahead. Yes, I was inviting them, yeah.
How do you, right, in these very high dimensional, I can understand how you can do this in for a scalar function of 2 or 3 variables, but how do you actually fill up these wells in your high dimensional energy landscape in practice?
You mean how you're sampling it enough to be able to fill it?
Yeah, kind of how do you know that you've actually done enough to be convinced that you found everything?
Sure. So there's 2 pieces to it, because you can either do it from a sampling perspective, right, where you've sampled all these configurations and you have all their energies, right? And it might be true that you might miss, right, features on the energy landscape if you don't do very good sampling. And those, I'm not going to talk about here, but those do show up as noise in the bar graph. And so you can see that. We actually have a comparison in our first JCP paper of a sampled energy landscape versus one that we constructed from the actual function of the force field itself. And you can see the noise that emerges as a consequence of the lack of sampling.
They tend to be fairly robust to this noise.
Yes, and I would say that it's also visually apparent when you have that noise. Yes. And you'll see why it's apparent in a minute, actually. Other questions? Yeah.
So now I have another one.
Oh, that's okay.
Some topology descriptors, they're smoothly varying?
Smoothly varying. Not necessarily, no. They're not necessarily smoothly varying, no.
Okay, so for a biasing perspective?
I hadn't thought about that. So we've used the graph, so for graph theory descriptors, you have to use a weighted graph, and then it becomes smoothly varying, and so that's why it worked from a biasing perspective for the graph theory descriptors. We have not used persistent homology descriptors from a biasing perspective.
Because even if I had a weighted graph, if I have a cutoff for my neighbors, then if I go outside the neighbor list.
Oh no, we created, in our weighted graphs, we do not have cutoffs there, so it is a smoothly varying function in that example, yes. Yeah.
The other one was on Tom's question. So in high dimension, if I can be a saddle point, very low energy. Then if I have any other uncorrelated perturbations of my system, I massively raise the energy.
Yes.
On the saddle point.
Yes. Yes.
So is that captured in this?
Oh, absolutely. 100% it is. Yeah, and I don't know if I have an example of that in the ones I'm going to talk about or not. There might be one. Okay. Any other questions at this point? I'm actually really glad I let you guys talk for a second, because I can kind of talk like a jackrabbit sometimes. So Okay. So now let's get back to our initial proof of principle associated with encoding energy landscape information with sublevel-set persistent homology. And so we did this initially for a series of small alkanes and we were just talking about conformations because we were just trying to prove that we could do this, right? And so we start off with butane and we get this sublevel-set persistent homology. We increase, keep on adding carbons, and you can see the higher dimensional features manifest themselves in the persistence diagram. And so then the question that we had, and in all honesty, that was, we asked ourselves a question in this first paper that we had in JCP, but we didn't fully answer it or make it completely generalizable. But we asked the question, what's notable about these barcodes in the context of the number of n-dimensional bars, and are there patterns that are emerging when we start to look as we systematically add degrees of freedom in these systems? And so, here's butane, and butane's got one, dihedral conformational degree of freedom. And in the barcode, right, the minima, this is the birth and death time features are, we've got our starting point, which is the birth of this feature, and we get the relative energy difference from the maxima and minima as the length of this bar. There's our other local minima. There's where our maxima were. So the barcode is encoding all of this information about the location of these features in energy space. And we can relate the configuration directly to these bars as well, because we know, and this will be more apparent in a couple slides because we're going to prove this in a minute. But initially, you can look at what all these conformations are, and you can see very distinctly which conformations are directly related to the position of the energy landscape. Now, for every carbon we add a dihedral degree of freedom, and so we increase the dimensionality of this conformational energy landscape. And so, one of the things we noticed in this first paper was that, the rotations of butane, we have the same rotations in butane as we have in pentane, we just have double of them, right? So all the rotations are basically translated copies of each other. And this is true as you add as many carbons as you want into this potential energy landscape. And so this implies that the potential energy landscape is a series of nested functions, right? If they're constructed in an additive way, okay? And I'm going to talk about this a bit more in a minute. But basically, if you are constructing or using functions that are not related to one another, right? So the dihedral angle of one grouping of atoms is not related to the dihedral angle of another grouping of atoms, then it turns out there is a mathematical way to prove the number of bars in whatever dimension you have, as well as the birth and death times of any N-alkane. And this is using something called the Kunith formula, and we're going to go through that, hopefully not too quickly, if I have enough time. And so the question is, if you use this Kunith formula and you use this idea of nested functions to build up an energy landscape, can I actually mathematically then predict the energy landscapes of new and unknown molecules? And you can. And so in our most recent paper, which just came out with Henry, we extended this to basically any additive function, irrespective of what type of degree of freedom that function was describing. And so you've got some energy landscape, which is embedded in R space, and it is needs to be a function over a product space. Okay, so these must be additive functions. But let's say that that energy landscape is composed of these building block functions, which are the ones that are added together. And these building blocks could be anything. They could be on the circle, like dihedral angles. They could be harmonic oscillators. They could be whatever you want, as long as they're all independent of one another. So let's just take, for example, 2-methylpentane. 2-methylpentane has a potential energy function that is made up of isobutane's dihedral angle as well as butane's dihedral angle. And you can kind of see this if we take slices, right, of the potential energy landscape for the conformational degrees of freedom of this molecule. If we slice along this dimension, it's slicing along butane. If we slice along this dimension, we're slicing along isobutane. And so basically, if we think about the sublevel set filtration for this molecule, it's a tensor product on the sublevel set filtrations of those building block functions themselves. And so what we decided to do is just take a whole bunch of different building block units and start creating more complex molecules. We did this for branched alkanes, but again, this is totally generic, and you could make this molecule as complicated as you wanted. So we've got our building block units. These are the structures of them, and the numbers are the degrees of those carbon atoms that are there. And we've got our building block functions. And then we've got the building block sublevel set persistent homology diagrams. And so if we want to generalize relative to our prior work, we know, and for right now for this example, we're still just dealing with conformations based upon dihedral angles. We know we've got n building block functions that are on the circle. We know the domain of our our total potential energy function, right? That's a result of that product space. And so basically we have an n-dimensional torus that has k-dimensional homology, and this is its rank. And so we can start to build up our mathematical proof associated with what the persistent homology topology will be. So the persistent homology barcode, all those features of whatever molecule we want initially based upon this. And so first we say, okay, well, how many semi-infinite bars do we have? So these are these bars that derive from the global minima on our potential energy landscape going all the way up to the top, okay? And we can prove how many semi-infinite bars we have. And I actually think I need to stop. I have 5 minutes now. Okay, good. And so then we can say, well, what about the total number of bars? The total number of the bars is the number of finite bars, which I just showed you, plus the number of semi-infinite bars, which are these guys. And so I know, basically, because of the torus, the circle that I have associated with all my building block functions, I can basically enumerate the number of semi-infinite bars that I have. And if I know that every building block function is a Morse function, then my total potential energy is a Morse function. And all that does is that mandates that my birth and death times correspond directly to critical points on that function. And so I can enumerate basically all of the number of semi-infinite bars, and I know that those semi-infinite bars have to be split evenly between the number of birth times and the number of death times that I have. And so I can immediately then determine how many critical points I have associated with my circle and my semi-infinite bars, which is all this guy is doing, okay? And so I now know I have 2 to the n semi-infinite bars and this number of finite bars. Now you can say, okay, now how many bars do I have in each dimension, right? Because I want to keep track of the dimensionality of my bars in order to map out the potential energy landscape. And this, I basically now I'm going to start using these building block function patterns that I'm leveraging. And so I can start with any building block function. Let's just say I've got my butane, okay? And this has 6 critical points, or 3 k equals 0 bars. So I know how many bars I have of dimension 0 and how many bars I have of dimension 1. And here you have to actually get a little bit kind of creative and you start with a brute force approach and say, okay, what mathematical function do I start to see? And then you prove that it's true. And Brittany was the one that did this because I think it required quite a bit of work on that front. And she's definitely the mathematical powerhouse as part of our team. But basically she showed that as you take these patterns from these building block functions, you can come up with a function and then prove that it actually is true. And so in the case of butane, she looked at butane and said, okay, this is the number, these are the number of bars I have associated with each dimension. And so she plugged this in and said, okay, I've got 3 bars of dimension 0, I've got 1 bar of dimension 1, that equation fits that distribution. Then she asked, does this equation hold as I add more building blocks? And she proved that it was true. Okay, so it's kind of an inverse derivation, if you will, starting off from the observation and going to the underlying formula that was leading to it. So now if you know the number of bars in each dimension and of the building block, then you can actually recognize that there's a finite number of ways to combine all of these bars to yield your new total potential energy function topology. And this formula is an older formula called the Kunith formula, but it basically provides all of the combination rules associated with finding all of the bars in every dimension. And so I'm not going to go through with that, but basically you're just going through the combinatorics, so going through all the math. But basically you can figure out the number of bars of each dimension k for a given set of n building blocks. And so here's kind of a nice example. Here's this 2,2-dimethylpentane. Here's the building block functions. And you can see all the building block bars are labeled for these functions. And we can say exactly what each bar in the total molecule derives from the combination of the building block bars. Okay? The cool thing about this is actually what connects you to the configuration of the molecule itself. These bars correspond to, oh, this is the maxima that occurs at 140 degrees or 180 degrees, right? So we know what all the geometries are of these building block functions, and now we know how they're combined, which means now we know exactly what the conformation is associated with every point on this persistent homology diagram. And we did this for much more complicated molecules. And the one thing I want to point out right here is, this molecule here doesn't look that complicated. It's a 7-dimensional dihedral angle potential energy landscape, but it has 840,000 critical points, 32 global minima, 186 index 0 local minima that are all under 1 kcal per mole in energy. It has 1,200 index 0 critical points. Sorry, those should be index 1 critical points before you, no, that's right. It has 1,200 index 0 minima before you overcome any of the barriers to the first transition states associated with those rotations, all under 2.75 kcals per mole. So this gives you an idea about how rugged this really, really, really high dimensional energy landscape is that we don't think about in this way. Now, if you know this, right, you can start thinking about, oh, how could I collapse all these minima into microstates, right? Once you collapse them into microstates, then you can start thinking about tools for them doing biasing or enhancing sampling and stuff like this. You can also understand the topology of how the potential energy landscape changes with substitution or chemical reactivity changes. And so by knowing the building block functions of my two reactants, I can determine what my topology will be of my new molecule. And so this provides a lot of new opportunities, and I think it's a really lovely way to directly connect structure to the energy landscape in a way where you've proven the energy landscape, you haven't actually had to sample it, but is based upon this notion of an underlying force field and those building block functions. It provides a way for us to learn about how the relative energies of minima and maxima are modified by changes in composition of the system or substitution in the system, which provides a way to potentially go towards experimental design strategies. How might you stabilize a specific structure or make sure the barriers ensure specific dynamic phenomena for an application of interest. You could use this in enhanced sampling techniques in the sense of now you know where all the barriers are that you want to overcome, and so you could start off with lots and lots of molecular dynamic simulations or Monte Carlo simulations based on different portions of the potential energy landscape. And so I think that this is kind of exciting. There are these limitations in that the proofs that I showed you were only for purely additive functions, but I think that there's ways around that as you get to more complex functional forms of the potential energy. And I just would like to say that if you guys are at all interested in other types of applied topology kind of approaches, Henry has this really fantastic YouTube channel called the Applied Algebraic Topology Research Network, which is quite good. And so now looping this into a soft matter design workflow, even though I'm not a workflow person, if I were to think about how I would do this, I would want to, and I think we're really interested and would like to get to a stage where we can, take synthesized and characterized data working with our experimental colleagues, do our structure analysis, do our potential energy topology, use this information then in some kind of machine learning framework with uncertainty quantification to help us make rational decisions about designing these soft matter systems. And so with that, I will just end with that turned out a little fuzzy, slightly fuzzy picture of Salt Lake City, and I'm happy to answer any other questions you've got. Thank you.